Oops. Can you see my full screen?
Yes, I can see it.
Okay.
Super. All right. So thank you all for coming. It's great to see you all here in person. Thank you, Surajit, for agreeing to give the second of 2 talks. I introduced you the last time, but I'll just briefly introduce you again. So Dr. Surajit Kalita is an NRF postdoctoral researcher at the Department of Mathematics and Applied Mathematics at UCT, working mainly with Amanda Waltman. He has a PhD in theoretical physics from the Indian Institute of Science in Bangalore, India, in 2021. This is your first postdoc. Really wonderful to have you here. You're an expert in gravity, compact objects, so on and so forth, which we're really excited to hear about today. So please take it away. Thank you very much.
Yeah, thanks everyone for coming, and this is my second talk. And in my first talk, I spoke about some very basics about how the compact objects are formed. I mean, what are the stellar structure look like. Primarily, I talked about white dwarfs and neutron stars, and what's there inside the white dwarf and neutron star, and basic idea. So so in this talk, I'll speak about more about some of my works and some, my works with all of these collaborators in different papers. And in this work, I'll touch about mostly about gravitational waves and how to understand some physics of compact objects, basically from white dwarfs and neutron stars, through gravitational wave observation in the future. I'm not talking about what people have already observed. And and towards the end, as I said, I'll be touching upon a little bit about noncommutative geometry, because I feel all of you are working on some quantum gravity stuff a little bit, and that's the closest thing I have ever done so far related to quantum gravity. And I'm a NRF postdoc, and I'm also a member of this Einstein Telescope group, which is being underbuilt in South Africa. They have like 256 radio telescopes, which will be operational in 3-4 years. So if you remember in my last talk, I spoke about like if our star, like a sun, say our sun, at the end of its lifetime, when it burns all over its hydrogen and eventually goes some intermediate phase, but eventually it becomes a white dwarf. But if the star is massive, its mass is much higher than our sun, then eventually, depending on its mass, it can become a neutron star, or if it's a much higher mass star, then its final stage can be a black hole. I've spoken about all this in the last talk, and if you remember, I talked about how the structure of white dwarfs and neutron stars look like. So to obtain the structure, basically to obtain the equilibrium structure, you need to solve basically 3 equations. One is called pressure balance equation, one is called mass balance equation, and another is called the equation of state. And once you know all these three equations, you can understand basically 3 variables now, P, M, and rho. And you have 3 equations with certain boundary condition. You can obtain the equilibrium structure of the compact object of white dwarfs. And if you know, if I told you for white dwarf, if you take basically exact equation of state for here, like which is basically proposed by Chandrasekhar in 1935, you can show that the maximum mass of a white dwarf can be Chandrasekhar mass, which is 1.4 solar mass. And as I told you also that a white dwarf cannot be stable if it gets more mass than 1.4 solar mass. And at that point, it bursts out to produce type 1a supernova. And type 1a supernova are very important because most of the type 1a supernova have similar behavior in the light curves. What does light curve means? Basically, supernova basically it rises its brightness or luminosity and then it decreases. So this is called basically the light curve. And it's similar behavior. What does it mean? It means first important thing is that how do you know that it's a type 1a supernova, because there are different types of supernova. In this type 1a supernova, the characteristic is that it doesn't have any hydrogen absorption line. but it has a silicon absorption line. And because of that, we define this kind of supernovae are type 1a supernovae. And if you see here, higher the peak luminosity, slower the declining rate. You can see, and this is basically something called Phillips relation, and which eventually used to get the idea of the standard candle to measure distances in cosmology, which is very important. And that's why this trend is very important, even though they don't have exactly same luminosity, but their trend is very similar, that higher the peak luminosity, slower the declining rate. But what happened recently in this Nature paper in 2006, for the first time they have observed something called peculiar type 1a supernova, over-luminous type 1a supernova. What does it mean? On this axis, it's basically luminosity, and y-axis is basically nickel mass. So what happens whenever a white dwarf bursts, it produces type 1a supernova, and most of the element actually basically something called nickel mass that you can actually measure from spectroscopy, and you can show that if the white dwarf bursts exactly at 1.4 solar mass at Chandrasekhar limit, the nickel mass present has to be of the order of roughly 0.9 solar mass. That's the maximum possible nickel mass produced. But what happens, they have observed that this type 1a supernova has nickel mass is of the order of say 1.3 solar mass. So it cannot be formed from a white dwarf which is burst at 1.4 solar mass. Similarly, not only this, there are like 15 or 16 so far have been observed, which actually looks like over-luminous type 1a supernova, which basically basically does not follow this basically there is another paper by Kokolov. He showed basically this is the maximum possible nickel mass. So it's much over this nickel mass has been produced by this over-luminous type 1a supernova. And not only this kind of type 1a supernova are also doesn't follow the exactly same trend of the light curve that I showed, that higher the peak and slower the declining rate. It's not the case. For this kind of supernova, it's even the higher the peak and the faster the declining rate also. So that's another peculiarity. It's not only the peak luminosity. So you can basically indirectly calculate how much should be the white dwarf mass to obtain that much of nickel mass or that much of luminosity. So you can do some kind of inverse calculation. You can show that all these basically 15, 16 white dwarfs at type 1 supernova have been observed. They have to be burst at white dwarfs roughly 2.1 to 2.8 solar mass. And clearly, in this mass limit, Chandrasekhar mass limit is strictly violated because it's much over than 1.4 solar mass. So then people started giving the theory. Basically, after this paper, or after roughly 2010, when people have observed like 4 or 5 of them, then people have started proposing some theory what can actually be possible reasons. So there are many theories, but I'll touch upon basically 3 things. One is these 2 things I have shown last time also very briefly, that rotation and magnetic fields, how it can increase the mass of any conductors, even for white dwarf neutron stars. And the second thing I'll touch upon this noncommutative geometry to understand. There are other theories, for example, modified theory of general relativity. You can also this thing, and there are many other theories people have proposed. So the problem is which theory is correct, we don't know. The main reason is that this mass is an inferred mass from the indirect observation of luminosity. You haven't observed such a high massive white dwarf from any direct observation. There are many surveys have been done, like SBSS data, Gaia data, but such high mass white dwarf have not been observed yet. Why is it so? Because you can show basically if you have say high magnetic fields, then you can actually show that the luminosity actually drops because higher the magnetic fields, then so lesser is the thermal energy. So it has basically less luminosity, and you can show that those white dwarfs are difficult to be detected even if they are there. So, so from electromagnetic observation, it's very difficult. So my proposal is that can we detect them directly? And I'll show that yes, this kind of white dwarfs can be detected directly if you use gravitational wave astronomy rather than our electromagnetic astronomy. And second thing, another interesting object which is called first radio burst, which I'm currently working on for last 1 year. So what are first radio bursts? These are basically radio events. That means this kind of events have been observed in radio wavelength frequency. and they are transient. That means they have been observed for a very fraction of a second. I mean, they are very fast. And typical range of this fast bursts that have been observed in radio by different radio telescopes over the world is in this frequency range basically people have observed. And it's fast bursts are typically one of the brightest event in the sky, basically in the universe, and its typical flux is of the order of Zensky. And what happens? This kind of burst, sometimes some burst seems to be repeating. That means you observe it today, maybe again tomorrow, maybe after some few more days. So those are basically called repeating fast bursts, whereas some apparently are not. That means they have been observed just once and they have never been observed again. And these are also recent events. And what people have confirmed, basically you need to calculate something called dispersion measure that you can observe. And from that, you can basically conclude that most of these fast bursts are extragalactic in origin. That means they are not, they were not formed in our Milky Way galaxy, except for one typical example, which have been observed very recently. These are the names of the FRBs. It's like, this is the day, this is the month, and this is the year. So it's 2020, April 28th, have been observed. So this is the only exception, but other than that, all other FRBs are confirmed to be, inferred to be extragalactic. And so far, like 700 or so have been detected. And this is also quite recent, like some telescope called SIME, like I showed you HIREX, that sort of it's been built. Its equivalent counterpart have already been prepared for the Northern Hemisphere in Canada. So SIME has detected over 600 FRBs, but if you just exclude the SIME FRBs, your number is just over roughly 50 FRBs have been detected by other radio telescopes. And expected rate is quite high, like per day you are supposed to observe that high. Once you optimize you can get all your telescopes to be optimized in that fashion. And the problem here is again, like now it's okay, 700, but people have been before this even number of models to explain fast burst phenomena, like over 50 or maybe hundreds of different models people have proposed, and which model is correct, nobody knows, because all of them can explain all of this almost, transient, flux, frequency range, and so. So this is the first FRB that have been observed in this science paper by Lorimer. It's famously called also Lorimer burst, and this is basically a dispersion measure curve. What does it mean? That basically your light ray, it consists of different frequency, and in the intergalaxy you have plasma. So when it travels from intergalaxy, different light rays travels at different velocities. So you obtain basically such kind of dispersion measure, and from this dispersion measure you can actually conclude they are extragalactic in origin. So again, here the problem you can understand, there are different models that have been there. So which model is correct? Again, nobody knows from the current electromagnetic observation.
So then the one that is not extragalactic, I guess you're saying that it didn't have this dispersion relation?
No, it has dispersion, but it's very low dispersion. Yeah. But other cases, it's much higher dispersion.
I didn't realize that these fast radio bursts were only discovered in 2007. So I thought they were around for forever.
No, it's been very recent.
Why do you think that is? Because it's radio, right? So why?
Yeah, it's radio, but you can see, but not all the radio telescopes observed are in this frequency range.
I see.
So most of so for example, most of them are not in this range. So whatever is there, and also this phenomenon is not quite repeating. Only SIME has been recently detected like 600. Apart from that, all the radio telescopes even after this have been detected just about 50 of them for last 15 years.
So it's rare.
It's very rare. And what happens now, you don't know which fast burst is coming at what amount of time. Today or tomorrow. So you cannot put your dedicated telescope for that, right, because other radio telescopes are dedicated for other missions. So that's the main problem. If you detect something by mistake, that SIME has been dedicated with this, so it has detected a lot.
Super, thank you.
So some physics people have done with FRBs. One thing that people have proposed, it's basically called primordial mass black hole mass fraction. What does it mean? you have dark matter. I mean, we propose there is dark matter, but how much dark matter is consistent of primordial mass black hole? Primordial mass black hole means which are not stellar mass black hole, if you remember my last talk. Which are stellar mass black hole means whose mass is of the order of mass of the sun. So apart from this, whatever other mass black holes are there, those are called those are not stellar mass black hole, and people have proposed they can be primordial mass black holes. And what fraction of dark matter are composed of this primordial mass black holes? So there are different limits people have proposed. For example, different experiments have proposed. There are a lot more. Actually, this curve actually goes much longer. I just took this much, and you can see from this first burst observation, people have proposed that, okay, say for example, 10⁻³ -3 solar mass black hole, its fraction is say 0.6. So it's 60% of the dark matter fraction is comprised of primordial mass black. So this is a very recent work. Similarly, people have given some constraints on photon mass. It's a little bit old paper. You can see this is basically the limit. And similarly, for Hubble constant, people have also given some limit of this kind of this solution paper. And not only this, people have also done different other physics also with FRBs. These are some 3 examples that I have given you that yes, many physics can be done with the observed FRBs, and people are doing this currently. So if you understand, as I said, basically there are 2 different theories there are very different theories that can explain FRB progenitors, basically how FRBs are formed. So primarily there are 2 theories. If you just take all the theories into groups, one is basically merger of compact objects, that means 2 objects merge eventually. And one is like isolated object. It doesn't have any companion, it's just isolated object. And some physics are related to this and some physics are related to this. So you can show that if you merge to compact object, for example, you merge to black hole, you merge to neutron star, or you merge to white dwarf, or one white dwarf, one neutron star, any combination of that, your final product can be a black hole or can be a white dwarf or neutron star. Of course, isolated black holes are also there, but I'm not putting this out here. What happens if you have a black hole, just a black hole, even it's rotating, it doesn't emit any significant gravitational radiation. I'm just coming in a moment. But if you have a white dwarf or neutron star, it can emit significant gravitational wave radiation, provided it follows some condition. I'll show what kind of condition. So let's first talk about this. For example, you have seen such animation quite a lot. For example, 2 objects are rotating around each other. They're emitting gravitational waves. They are coming closer and closer, and at certain point they merge. And when they merge, they eventually, suppose they become a black hole. And you can see even at the beginning, you have basically. So at the beginning, it's emitting gravitational radiation. But eventually, when it merges and it becomes just one single object, say a car black hole, a rotating black hole, it doesn't emit any significant radiation, gravitational wave radiation. So, and when it merges, basically some electrons are traveling with some magnetic shocks are there, and it deposits some energy in the magnetosphere. And you can show that that energy we see as a first radio burst. So this is one explanation how merger theory can explain the origin of first radio burst. What is the second theory that I'm going to say about the isolated compact object? Basically, I'm just going to say one particular type of effect, which is called Garstein-Zel'dowicz effect. There are many different mechanisms here also. What does it say? It's very simple. You have an infall gravitational wave, and you have a pulsar. Say, for example, here, it has pulsar means it has some magnetic fields. It has basically this is called light cylinder, where the magnetic fields are mostly confined. And the gravitational wave falls here. It interacts with the background magnetic field, and output, a part of the gravitational wave, can be converted to electromagnetic radiation. How much it converts depends on the strength of the magnetic field, but the effect that gravitational waves convert to electromagnetic radiation through magnetic fields is called Garstein-Zel'dowicz effect. And this effect is also reversible. For example, if you fall in electromagnetic waves, you can also get gravitational wave radiation. And you can show that, for example, gravitational waves, as I showed in my last talk, that it has two polarization mode. One is called plus and one is cross polarization modes, which has a phase difference of 45 degrees. So if you have this gravitational waves, it has a frequency of say omega g, and you have a pulsar which is rotating at omega rotation frequency. So its magnetic fields are also rotating at this frequency called magnetosphere. You can basically write your Maxwell equation, but not Maxwell equation in flat background. Rather, you have to take the curved background, Maxwell equation in the presence of gravitational waves. So you have to write the Maxwell equation curved background, and you can show that the output electromagnetic radiation follows these equations. And these are basically the terms which have basically frequency of omega plus minus. So you can see omega plus is omega g plus omega rotation. That means output electromagnetic radiation has a frequency contribution from the infall gravitational wave and the magnetic field frequency. So all the pulsar frequency. So and this basically this is basically the output electromagnetic wave radiation. So what does it say? So for example, we cannot see, say our radio telescope is here, and at certain points, say some gravitational wave falls, the telescope cannot detect gravitational waves. But all of a sudden, you see from that position of the sky, some electromagnetic radiation comes out. And if you can match this electromagnetic radiations, all the properties, for example, its flux and time scale, all these things, you can show that this electromagnetic radiation behaves as a first radio burst. So it looks like, what does a burst means? Burst means all of a sudden you see a sudden flash of light. And here also because you don't see this radiation, you see just this blue radiation, and you see all of a sudden it just comes some blue radiation from the point. And that's what we basically say, or basically said that this is the first radio burst. And of course, I'll show towards the end how to match this electromagnetic wave radiation with the pulsar property, and so that it matches with the observed first radio burst. But this is one of the mechanisms. So you can understand, I have spoken about two particular differences. One is basically super-Chandrasekhar white dwarfs have not been observed directly, and another is progenitor theories of FRBs are not known. So, and that's the main problem. And how to address these two issues are the gravitational wave observation. So all these things I showed last time, that different physics as I wanted to show. One is basically called rotation, effect of rotation on white dwarf and neutron stars. So rotation can increase the mass of a white dwarf and neutron star. So in 1968, Austrian Hartwig showed white dwarf mass can go up to 1.8 solar mass. Similarly, this German group has shown that neutron star mass can also increase up to 1.2 times than its original value in the presence of rotation. And rotation can also change its shape of the star. If it's a spherical, because of the centrifugal force, you get eventually an oblate shape star. And similarly, magnetic fields, depending on the magnetic field configuration, you get different shape of the star. For example, you have a spherical star. Now, suppose you have this kind of magnetic field, which is basically toroidal magnetic fields. Your magnetic field pressure are in this vertical direction. So you're eventually, the shape is more of an oblate shape. But if it's a toroidal like magnetic field, that means your magnetic field are looking like a torus. So your effective pressure is from the equatorial direction. So your extra pressure is coming from equatorial direction, and you get this kind of shape of the star. Now, suppose on the top of this, the star has a rotation. So depending on whether the rotation is significant or whether the magnetic field is significant, so eventually the outside shape can be an oblate or prolate, depending on which one is dominated. And you can also show that in the presence of magnetic field, whether it's polar field, toroidal field, doesn't matter, because of increased magnetic field pressure, you can actually show that mass of the compact object also increases. And this can also explain those super-Chandrasekhar white dwarfs.
So can you explain this a bit more? So what's the red, green, and blue?
Okay, so one is basically the toroidal magnetic field configuration. Green one is the colloidal field magnetic field configuration, and the red one is some mixed field configuration between the two, suitably utilized. Because purely toroidal and purely colloidal field magnetic field configurations are unstable. You can show from stability analysis. So what the actual object has, it always has a mixture of these two components. So, but whatever be, always the mass increases with the increase of magnetic field.
And so I don't have a good finger feel for 10 to the 14 Gauss.
Yes.
Where does it start to become unphysically large as a magnetic field?
Yes, I'll come to that also. But yeah, let me talk to you. So to obtain, basically, if you have less than this much magnetic field, you basically don't get any increase of the mass. And you can understand this field is quite higher than the basically Swinger magnetic field value. Also. So it's higher than Swinger magnetic field. So you need basically higher than Swinger magnetic field. Now, from some people have shown from some stability analysis that the maximum, this is basically called magnetic to gravitational energy ratio. So how much it can be? It cannot, definitely it cannot be more than 1. That's for sure, because magnetic energy cannot be more than gravitational energy. But how much it's maximum? So different simulations have been done. So different group has proposed different limit. Some people has proposed 0.1, some people have proposed like 0.05. So you can put some cutoff here. And that's why this magnetic field always has this kind of issue. And to address this issue, I'll show that noncommutative geometry eventually can actually replace this magnetic field idea, and it doesn't have any problem of this stability analysis. So now I have this isolated object that I showed in a couple of slides back, and if it behaves like a pulsar, that means its rotation axis and the magnetic field axis are not inclined to each other or aligned to each other, then it can emit gravitational radiation. So to emit gravitational waves, the thumb rule is that the system should have a time-varying non-zero quadrupolar moment. If your rotation and magnetic field axis are in the same direction, this is 0. So you need always a non-zero angle between these two axes. And you can show that the output gravitational waves, because of this configuration, is basically emitted at 2 frequencies. That means if it's rotating at, say, 1 Hertz frequency, the output gravitational wave has 1 Hertz as well as 2 Hertz frequency. And you can also understand if chi is 0, then all these amplitudes are 0 basically. And of course, it's inversely proportional to the distance. As you go far and far, amplitude dies down. And when you detect something, you need to, for the detector, you need to know the signal to noise ratio. And basically, because it's emitting at 2 frequencies, your signal to noise ratio has to be a superposition of these two. And you can understand D is the time detection time. As you detect something for more and more time, longer time, your signal to noise ratio increases, and once your signal to noise ratio increases, that object is more probable to be detected. So that's some mathematics. And that means, to summarize, that I have shown that rotation, toroidal field, and colloidal field changes the shape of the object, but that rotation and magnetic field should not have same alignment. And once you do not have same alignment, you don't have, basically, you no longer have a spherical symmetry, you no longer have an axis symmetry system. And the problem is you cannot simply solve dPdr and dmdr equation because you don't have this. So you need to use some kind of simulation code. I use this code, basically, this Italian group has developed this code where you can suitably put all these magnetic fields, different kind of magnetic fields with rotation, and after running the code, you obtain basically the structure of the object. So, and before I go to the gravitational waves, I showed also in the last time this figure that these are different detectors, except this LIGO Virgo, all other are underbuilt or proposed detector. So you can see these detectors can detect gravitational waves which have frequency more than 1 Hertz. And LISA will be launched in future, and this BBO and DECIGO, all this will be launched in future, similar Einstein Telescope. And you can see they have different frequency range. Some of them are less than 1 Hertz, some of them are more than 1 Hertz. And depending on that, it can detect different objects. For example, these detectors can detect, say, neutron star pulsar or this compact binary inspired. Similarly, these detectors can detect binaries, white dwarf binaries in our galaxy and so on. And these are some pulsar timing array detectors that have also been built.
I'm sorry, so I just want to pause on this for a moment, if you don't mind. So first of all, SK, is that the square kilometer, right?
Yes.
How are they going to measure gravitational waves?
Oh, because it's pulsar timing array. Because pulsar timing array means you have a pulsar, you have different frequencies will also.
So it's not going to be direct detection.
Yeah.
Okay. And then, okay, so LIGO is what exists now, right?
Yes, LIGO, Virgo, Agra, this three exists.
Okay, and so if we trace the LIGO curve down,
Yeah.
so it just barely hits the compact binary in spiral. Is
Yes.
that
Yes.
much? And then where's,
So see,
okay, so that was like what they detected the inspiral and then it formed a black hole. That was
Yes.
what they.
yeah, but for that your black hole, binary black hole should be near enough. If it's far enough, your this amplitude will go down like 1 by r.
Right.
So it can, that's why it cannot detect. Similarly for pulsar, that's why it cannot be detected by pulsar. If the pulsar are nearby, if this will be going up, then it will be.
Great. Thank you.
So now I will come to the results section of my first part of my talk. And suppose I put some magnetic field, say colloidal magnetic field for the first case. And if you put colloidal magnetic field, suppose your magnetic field is I should write this. It's colloidal B. I should write it's surface magnetic field basically. Suppose your magnetic field, and these numbers are also wrong. Sorry. This because so but you can understand if it's colloidal magnetic field, if it's a low less surface magnetic field, then see, for example, BBO and DECIGO can detect, say almost instantaneously, but these detectors cannot detect even within 1 year or even more than that. You can just extrapolate this stuff. Similarly, if it has higher magnetic fields, then also it cannot detect if it's a colloidal field magnetic white dwarf. But if it's a toroidal magnetic field, I just put this number on the other slide. Sorry. But if it's toroidal magnetic field, you can show that even like BBO DECIGO, if you remember in my earlier slide, BBO DECIGO is much above, so it can immediately detect. But these three detectors are down, and anything that's above this orange line can be detected. Here, even Alia said this detector can detect, but not Lisa. But if its magnetic field is higher, that I showed last time, it's roughly 10^14 Gauss, if that magnetic field is allowed, then even Lisa can detect that magnetic, that white dwarf. So it's like if Lisa can detect that white dwarf, we can immediately say that, okay, so magnetic field that much is possible. So that magnetic to gravitational energy ratio that much is possible. So if it cannot detect, then we can also put some restriction even from that. Similarly, for these FRBs, as I showed, FRBs means gravitational waves are passing through, and a part of it is converted to electromagnetic radiation. And this green wave is separately from this itself from this pulsar that I showed basically, which has two frequencies, omega and omega. So this gravitational waves is not this gravitational wave. This is due to the pulsar. It's generated from here, but this is something coming from the other part. And suppose I consider an FRB which says of this, and these are some observed properties I can observe for this. You can show basically if it has pulse width of this much, what does pulse width will tell? Basically, pulse width will say how much time it will take basically to cross this light cylinder. And you can just calculate all these things. And you can show that basically this is the rotation frequency, this is the linear frequency, and you can see it's less than 1 Hertz frequency. So it can be detected by not LIGO, but by DECIGO on the space-based telescope. And you can also match the flux of the gravitational flux of the electromagnetic wave, and you know all the other factors except this uniform gravitational wave amplitude and the pulsar magnetic field. So let's assume that it has A+ is of the order of this, then magnetic field turns out to be this. If you lower the A+, B1, I mean, the surface magnetic field will go high. But I have just taken this example just to show that if this is possible, this much magnetic field, surface magnetic field is possible by both, I mean, by both white dwarf as well as neutron star.
Sorry, where are you going?
I'm sorry.
Why minus 51?
Oh, it's just calculate. You just need to do E cross B from here to get, and then you get this thing divided by 8 pi, and you just need to put all the numbers.
But 51, you sure?
Yes.
It's just, it's the integer 51.
That's also a question. The red gravitational wave, where is the idea that that's coming from?
Yes, that's okay. Oh, I forgot to say. If you remember, my outward electromagnetic wave has a frequency of omega g plus omega rotation. And we know that output gravitational wave has output electromagnetic signal have been observed at say 111 megahertz frequency. Now we know that omega rotation should not be more than kilohertz frequency because it's a star is rotating. So it's megahertz, it's kilohertz. That means this has to be megahertz frequency. And megahertz frequency cannot be achieved by any astrophysical source. So it has to be some cosmological event has to happen. So people have proposed different events. So for example, merger of two primordial mass black hole or in spiral of two primordial mass black hole, and some others like oscillons reheating media from the early universe. So all those gravitational waves has to be here. It's basically cosmological wave.
And then just one other thing. So these pulses, so these are very small. Like it's happening very quickly. The pulse that you see
Yes.
is that from because the gravitational wave, the red one, is that also very
Yes,
short?
yes, it has to be. Or the second, one more thing I forgot to mention. This GZ effect is only applicable when your infall gravitational wave is perpendicular to the magnetic field. I mean, this direction has to be perpendicular to this. Now this pulsar is rotating. Say it has rotated. Say part of this, even though this gravitational wave is continuous, so it's falling continuously. But because the pulsar is rotating, it will not convert every time to this much amount. Only when it's the maximum amount is possible. Only when it's the perpendicular. Otherwise, you need to take the projection of that amount of magnitude.
You said that there was at least one FRB that's repeats, right?
Not one. One is galactic. There are many FRBs, like a few of the, I think 15 or so have been observed to be repeating.
So what would be a gravitational wave source that repeats?
This gravitational wave source.
Yeah.
Yeah, this can be anything. So, for example, in spiral up to primordial mass black hole, emitting continuously the frequency. Very light black hole if to consider to get megahertz frequency.
But and what there's so many of them that it's just gonna we get repeats of this FRB.
Yes. So you don't need so many, like you observe, say, from this direction, so that infall gravitational wave has to be on that direction. If something is in that direction, then only you can see. You don't need to see in the other direction. That's
It seems rare, but okay.
I mean,
Yes, it's an in-spiral event. How long does that take?
Right, yeah.
I mean,
no,
a single in-spiral
Yeah.
event.
for-
How long does that take?
yeah, for example, say this, you can see this frequency is obtained by basically massive black holes. When it's less massive, like stellar mass black holes are rotating, and it emits of the order of 1 hertz frequency. I mean, this much. And if it's lighter and lighter than the stellar mass black hole, less than 1 mass, then it goes higher and higher. And you can show that this is megahertz. Basically, you obtain basically this obtained by small.
Well, that's the rotational frequency of the thing, right?
Yeah,
As
that's
they-
the
as
install
they-
frequency.
As
Yes.
they come.
Yeah.
But how long does it take for these things to hit, right? From the time where they start
Yeah.
radiating until
Yeah, of course,
it
it's not
stops.
observed. It's the only
So
thing.
how long does this?
See, inspiring can happen for long enough time. Merger will happen just for a quickly for a second, but inspiring can happen so for years or
For you?
thousands of
Okay.
years.
Okay. Yeah, okay. Just asking for.
Yeah, yeah, sure, sure.
We have megahertz gravitational waves. These things are going around each other at megahertz frequency for years.
Yes.
That's wild.
So yeah, here also you can show that if the object that FRB this 160920, if it's a white dwarf, because this magnetic field can be attained by both white dwarf and neutron star. If it's a white dwarf, then some detectors can detect, and similarly some, I mean, depending on which. And here you can see, like, we don't know the distance of that object, because that's the one big problem, that we know those are extragalactic because of high dispersion nature, but you don't know exactly what is the redshift of the object. So I have just roughly calculated, say it's from 100 kiloparsec to 100 megaparsec distance. So still you can show that LISA can no longer detect, because to LISA to detect, even if it's a 100 kiloparsec distance, it requires 10 per 4 years. But say if it's at say 100 kiloparsec I mean 100 megaparsec distance, then even say, for example, BBO or DECIGO can detect within 10 years observation. Similarly, one more example I took, I'll not spend much time. It's a different FRB. It has been observed at different frequency, pulse rate is different. And why this is this I have chosen, you can show that its rotation, if this GZ effect is important, then its rotation frequency is 18 Hertz. So it's no longer now LISA range, now it goes to LIGO range. And you can show that advanced LIGO or Einstein Telescope detectors can detect appropriately how much time. So this comes to my conclusion of the first part, that GZ effect is one of the theories which can explain both repeating and non-repeating FRBs. Why this is important? Because you see some FRBs are non-repeating, some FRBs are repeating. So if you can only explain some theory which can explain non-repeating FRBs and not repeating FRBs, those theories should not be valid. I mean, if we assume that one theory can explain all the FRBs. In that sense, GZ effect is good one, because it can explain both the type of FRBs. And of course, it's difficult to single out the exact theory from the current radio observation, and GW observations can differentiate between the merger and the isolated object. For example, as I showed, if the merger and then finally it becomes a black hole, and that FRB even have already been done. Now, even if we put our detector, our gravitational detector in that direction, so we will not detect any more gravitational waves. But if it's an isolated object, for example, a rotating white dwarf or from a rotating neutron star, and everything is within our capacity, our instruments, then it can also emit gravitational waves, which we can detect also. So it can differentiate. So gravitational waves detection can differentiate between merger and isolated mechanisms. And also it can detect, say, whether they are white dwarf, neutron star, or black hole, as I showed. So if it's white dwarf, then some detectors can detect. If it's a neutron star, then it cannot be detected. So this concludes my first part. Now, earlier I told you about the super-Chandrasekhar white dwarf, which had different theories. And I told you, like rotation and magnetic field, I showed you how it can increase the mass. I have also said that modified gravity, which I will not speak today. But I will be speaking about something called noncommutative geometry. So how to get the idea of noncommutative, or how we implemented it. So let's get the idea of magnetic fields again. What I said so far about magnetic fields is about shape and size, changing the shape and size because of the magnetic field pressure. And so that's more like a macroscopic effect. We put magnetic field pressure. But it has also a microscopic effect. Because of magnetic field, you can get the lambda levels formation in a plane perpendicular to it. If it's magnetic field in this direction, you get this kind of lambda levels. And the energy dispersion relation looks like this for this lambda level. Basically, in this magnetic, this is in the z direction. So this is I mean, what is basically E square this relation? E square is equal to P square C square plus M square C power 4. P square can be written in 3 parts: Px square, Py square plus Pz square. But because this lambda level is formed in Px-xy plane, so Px, Py eventually give you this kind of quantization, which looks like basically this, and you can understand this B is the magnetic field, and this is basically called the Swinger magnetic field, which is of the order of this value. And you can show, even with this thing, you don't need to change anything. You just consider say dn as it is, and you just take this dispersion relation and you obtain the equation of state from here, relation between P and rho that they have done in the spiral paper. You can show that eventually the mass of the white dwarf can also increase 1.4 to 2.6 solar mass. So this is the idea we have borrowed to get our physics for non-commutative geometry. What does in non-commutative geometry say? So we know in ordinary quantum mechanics and Heisenberg algebra, we know that momentum commutes, position commutes, but position and momentum, conjugate position and momentum do not commute. It's very similar, but in non-commutative geometry, it's very similar to magnetic field. These are very schematic idea. For example, suppose my non-commutativity is only in the XY plane for the time being, I'm just assuming. Then this plane is non-commutative. It looks like a magnetic field, but it's some kind of not an external magnetic field, but some kind of, you can say, space-time magnetic field, which has the internal structure. But suppose your YZ and ZX plane are still commutative, they will follow this kind of algebra, but XY plane will follow this kind of algebra. Theta is basically the non-commutative parameter. But this is not a very good thing, because how can one plane be non-commutative and other plane be commutative? That's, I mean, if it's internally generated. So if it's non-commutative, all three planes should be non-commutative. And to address that issue, this basically we get the idea of fuzzy sphere, which has been proposed in 1992. It's coming from the idea of angular momentum algebra. So you basically take the angular momentum algebra, this cyclic algebra. These are angular momentum generators of angular momentum. And you in the fuzzy sphere algebra, it's very similar, where you basically just replace this with the position coordinates, basically x, y, and z. And eventually, earlier what I have showed that x, y is something. Now x, y looks like basically this kind of cyclic form. And this formalism is called fuzzy sphere formalism. And this is basically one fuzzy sphere where basically all three planes are non-commutative. Now, later these two guys have given another idea called squash fuzzy sphere. What does it mean? You project all the points of the sphere to an equatorial plane. So for example, XY plane in this case, then this plane will become non-commutative, and what your algebra will look like, you can write basically x1, x2, and because you project all the points here from the equation of the sphere, you can write this x3 in terms of this, and plus minus whether you are projecting from up or down. And basically this is called squash fuzzy sphere algebra. And why it's good? Because as you come out and out at the surface, it's zero basically. So you can recover your commutative algebra. And we have used this algebra. Eventually, okay, it's very important that this plane doesn't matter whether it's x1, x2, or x1, x3, x2, x3, or any other combination. So eventually it doesn't matter. So what you need to do, you take this algebra, and we can write basically that we need to figure out the energy dispersion relation. You can basically write this Casimir operator and all these things. I'll not go into detail because of the time, but you can eventually write something, a Dirac operator, because I have squashed it in the x1, x2 plane. You can write the Dirac operator in this form basically, and the square of the Dirac operator, if you write and if you take values, you can show that the eigenvalues looks like this. So, and here it's important, when you write, basically you take the square of the Dirac operator, you get basically sigma 3 polyspin matrix, the third one. But if you take, for example, initial squash plane, say x1, x3, then you write generally sigma 1, sigma 3, and your square will give you sigma 2. And it doesn't matter because all the polymetrics has the same eigenvalues. So eventually you get this plus minus 1 for all of them. So this energy dispersion relation doesn't matter whether we project in a whatever plane we want. And from here, this is just the energy dispersion relation. And from here, you can just write with the help of proton, say electron is traveling, suppose, then you can write this total energy dispersion relation. And you can take some limit because in our physics, we'll be applying it to such wide dwarf neutrons with some very big in radius. So some number n is basically n by n irreducible representation. Any SU2 algebra can be written. So that n, and you can take some limit, and you can show that basically this energy dispersion relation comes to this point, and which is very similar to the magnetic field. The magnetic field equivalent of the magnetic field, and you can understand here that always the ground state is singly occupied, and all the higher order states are doubly disaffected. And this is the quantum number. And from here you can write basically Fermi-Dirac statistics. As you remember, I told in the last talk that in zero temperature Fermi-Dirac statistics, you have this kind of integration. But now, because you have an quantization, this integration can be written in this summation form, and you have basically this formula. So eventually you can write basically pressure and the density relation from here, from the energy dispersion relation. And you can understand basically this is the summation. This means how many energy levels are filled. As you see, it's basically new how many energy levels are filled. Depending on that, this number will change. And this is my new energy. This is my new equation of state. And if you just plot that equation of state with different occupancy, say only ground level is filled, only first, two levels are filled, and then 3, and so on, you can show that this is the Chandrasekhar equation of state, and this is the equation of state, modified equation of state, when you get basically only the ground level is filled. As you start filling more and more and more, this curve eventually merges because it becomes more and more classical after some point. And with this help, you can just solve this P and rho relation with dpdr dmdr equation, and you can obtain basically this kind of radius curves, and you can show that 1.4 solar mass white dwarf can be now much more higher than that. Basically, you can explain the super-Chandrasekhar white dwarfs with the help of this non-commutative geometry. So why this non-commutative geometry is important and what length scale is important? So this is just an idea I want to give from a thought experiment given by Whitner much earlier. So suppose you have a light ray here, and it's traveling from A to B, a distance of L. So if it has a pulse width of delta, when it reaches B, it will eventually have a pulse width of this much, basically uncertainty length. You can put on, you can see the derivation. Basically, L by C is that this time required to light to travel from A to B. And from here, you can show that this function has a minima when delta attains to this. That means delta square is always greater than this number. And from GR, we know that any information can be obtained if it's outside the event horizon. So delta has to be greater than GM by C squared. So you just combine these two relations, and you can show that the uncertainty length scale not only depends on the Planck length, but also on the system length scale. So it's the combination of both of them. So how does it important in our case? You can, this is the energy dispersion relation, and you can understand non-commutativity is prominent whenever numerator is higher than the denominator. And this can be written in this form. That means your length scale of the system has to be less than the Compton wavelength of the electron. So our general thought is non-commutativity is prominent at the Planck scale, but if you have a collection of particles, say for example, collection of electrons, then the new uncertainty length scale is no longer only the Planck scale, but it's a combination of the system scale and the Planck scale. So in our case, all the mass radius curve, you see from where it starts deviating, exactly from the point when your system scale, the system scale means in our case, in our white dwarfs, it's basically inter-electron distance. So inter-electron distance is less than the Compton wavelength of the electron. So whenever this condition clicks, that means inter-electron distance is less than the Compton wavelength of the electron, then your non-commutativity effect starts becoming prominent. Otherwise, you go back to your commutative physics, or it's becoming insignificant. So similarly, for neutron stars also we have calculated, and okay, I didn't know, but you can also obtain different mass radius curve in the neutron star physics. So basically, this is my last slide to show the conclusion that gravitational wave observations are very important, as I showed in my first part, to understand the physics of compact object. And gravitational wave observations can differentiate between the merger theory and isolated compact object theory for the production of fast wave bursts. And there are different gravity theories. There are different theories which can explain the massive white dwarfs and massive neutron stars, and which theories we don't know. And gravitational wave observation in the future can directly detect if it can provide some information about these theories, or for the theories of FRBs, which of them are correct. So yeah, that's all. And yeah, Amanda also wanted me to tell about that. We have some projects, and if anybody wants to do, you're most welcome. Thanks.
If we are cutting that, then you have to say for the YouTube audience to smash that like or subscribe button. Super. So we had some questions on the way, but are there any more questions?
I came late, so maybe I missed it, but for the non-squash, non-commutative geometry algebra, why do you constrain yourself to the surface of the sphere again?
Can you just repeat the question?
So maybe I came late, maybe I missed
No,
it.
it's fine.
Or can you go back to the slide with yes, this one. So for the fuzzy sphere algebra, squash fuzzy sphere algebra, why do you constrain yourself to the surface of the sphere rather than the squash fuzzy sphere algebra?
We are using this. Why we are using this? Because at the surface, you automatically, this is zero. So outside, basically, you have your commutative physics. So only non-commutativity is inside of an object where you have matter. So outside in the vacuum, you don't have, you obtain your commutative algebra. Even in the inside, where it is prominent, you might have non-commutativity everywhere, but it's not prominent. It's prominent towards the center, where basically that length scale argument I said, it's less than the quantum argument. So only at that reason, if that reason is large, it's small.
Okay.
And what's the physics motivation for why there might be some non-commutative geometry happening?
Okay, that's what I said about the length scale argument. I said. This is a thought experiment they have used earlier, where basically you can show that the uncertainty length scale is a combination between the not only the Planck scale but also the system scale. And this is what they have used. Now, in your case, you can show from your energy dispersion relation with this formula that your length scale is less than Compton wavelength of the electron. Then only this effect is prominent. That means this factor is prominent. You just basically this factor has to be prominent, numerator has to be greater than denominator, and this can be written in this form. This is just a number, ignore this. But this is basically the condition. Now, what is length scale in a system? Length scale means in our case it's inter-electron distance because electrons are comprised here. Or for neutrons, it's say whatever particle is here, the inter-particle separation. That means whenever its inter-particle separation is less than the Compton wavelength of that particle, only then your non-commutativity triggers. Its effect is significant. Otherwise, it's insignificant. And that's how your new uncertainty length scale has to be a combination of Planck scale as well as the Compton wavelength of the particle. Because it's a collective of lots of particles. It's not a single particle system. Because you have lots of particles, and basically people have used something called dressing of particles. So it's like all the particles are dressed up to occupy more space. What your general commutative quantum mechanics say, that's, for example, in this mass, this many fermions are possible because of its property. But in non-commutative geometry, you can say that, okay, it can accumulate more particle in there because they are dressed up, and that way it's basically density increases.
Yeah, so thank you. I don't think maybe I didn't communicate effectively my question. So none of the physics that we are aware of is non-commutative, right?
Yes.
So the fact that you're putting in a Planck length there just maybe saying that maybe quantum gravity is a non-commutative geometry effect.
Yes, so for quantum gravity, there are different theory people have proposed. For example, this quantum geometry, something called asymptotic safe gravity, some people have proposed generalized Heisenberg uncertainty principle, which is a little bit higher order correction. It's called Heisenberg uncertainty principle on the right side. And there are different other people have proposed different mechanisms. These are basically modified gravities, modified theories of quantum mechanics.
Okay, but is there any motivation for why we might expect physics to behave in this way?
It's basically, see, in astrophysics, nobody explored. This is the first thing that because these high massive white dwarfs and massive neutron stars have been observed, and you can understand the problem with the magnetic field theory that it might become stable, unstable, and so. But if you use your noncommutative geometry, it doesn't have any macroscopic effect. That means it doesn't exert any magnetic field like pressure, torsion, all these things. So it can explain them. So that's one indirect observation way we have proposed. But other than that, people don't see any other effect, because other than that, whatever paper I've seen, people have just used black hole physics to explain, say, event horizon. So from event horizon telescope, you use some non-commutative geometry, you modify your short sight metric, and in non-commutative geometry, you can show basically your short sight metric is modified, and then you can modify all your event horizon radius, orbits, and so on. So from there also people have proposed that, okay, this can also explain that particular phenomenon.
Okay, but is there any fundamental theory that we might think would explain, say, quantum gravity that predicts non-commutative geometry?
So I don't know.
Get nervous then because theory space is infinitely large, right?
Yes. So that's why basically, like, not only this is of course one exotic physics, I would say, but there are other exotic physics other people have proposed to explain the massive void distribution. So how to get rid of all this physics? So with the current observation, nobody can rule out. But yes, with the future, because what happens from the current observation, we don't know exactly the mass and radius of that object, of the massive void. Now, because we don't know exactly the mass and radius, so each theory gives you different mass radius curve. Say, for example, this theory gives you, say, for example, non-commutative geometry gives you this kind of mass radius curves. If you take a different theory, your mass radius curves also changes. So which mass radius curve is correct, we don't know, because all the white dwarfs that have been observed are in this low density region, basically, massive. So, in this, less massive white dwarfs. So massive white dwarfs and more dense white dwarfs are still not observed. So you don't know. Okay, for example, we know this green line is ruled out, but you cannot rule out, say, for example, red and black line with the current observation. So you need more and more observation to constrain the mass radius. And how to get that with the gravitational waves is prepared.
Thank you. Other, yeah.
So going back to your rotating composite object that has its specific orientation on a magnetic field.
Mhm.
In a physics sense, I'm kind of trying to wrap my head around. So you have an incoming gravitational wave,
Mhm.
which is gravity, and it's having some gravitational oscillatory effect on the object.
Mhm.
And then you're now saying that leads to an electromagnetic phenomena change. So in a physics sense, how do we kind of understand this link between this gravitational effect on your object and how it then changes how it emits?
Yeah.
its
So
electromagnetic
okay.
radiation?
Yeah. So basically, for that, as I said, you need to solve the Dirac equation here. So what's Dirac? Not Dirac, it's a Maxwell equation. So for Maxwell equation, in flat space, then we know it's del mu f mu, and its dual is, they are zero. But in curved spacetime, you no longer have the partial del mu. I can write.
In a gravitational covariant.
Yeah, you need to write basically something called del mu, which is basically partial your ordinary del mu minus some connections terms will come here. And not only this, you have to now write your Maxwell equation. Initially, it's del mu f mu nu equals to 0, but now your gravity is this minus g factor is coming here. What does it say? Why is it coming here? Because if you now assume from here, your background has gravitational wave, so it's no longer a flat space. It has some curvature, even if it's small, and that curvature is included with this minus g and with these connections.
Okay, I see. So in a more intuitive way, it is in curved space, and
Yes.
your gravitational wave is gonna affect.
No, gravitational wave is itself created by curved space. Your magnetic field is on the top of your.
Yeah.
Uh,
Yeah, right, magnetic field lives in this changing space-time, right? And that fiddles with gravity,
yes.
with magnetic fields through that sort of thing.
Okay, but, okay, not but, that shows kind of. Doesn't that show some link between how we understand gravity and how we understand like magnets?
Well, generically, this is always there, right?
Yes.
It's just that when you do electrodynamics for, I don't know, everyday gadgets, there is no, you can forget about the curvature.
Yes.
It's so tiny that it doesn't matter. So
Okay,
in principle, you have always have to write something.
okay.
It's just for everyday applications.
Yeah.
Forget
But
about
that's effect is small because we live in a non-limited space, but that's really nice.
but that thing, of course, right? There, gravity gets
Yeah, no, definitely.
gets to a different scale. Curvature, I mean, this is curvature gets big.
So the change in curvature then affects your Maxwell equations,
Yes.
which is gonna change how.
Generic.
Okay, I see.
How to generically estimate, of course, how big this has to be for an appreciable effect
Yes.
is probably a little tricky. I'm guessing you've done this for.
Yes, this
specific
is for
examples.
the quick field.
Yeah.
You just need to write instant form.
Yeah.
Flat space will be g mu nu, eta mu nu plus h mu nu, and then basically flat plus some perturbations.
Last questions.
Actually, just going back to the fast radio burst, you said that this GZ stuff predicts it can do well the repeating and non-repeating. So I think yeah, from what I just correct me if I'm wrong, but the way I'm understanding is that the gravitational wave has some frequency that's coming in.
Mhm.
Is that what sets up the repeating?
No,
No.
no. It's
So we're
basically
getting much
whether
bigger.
for repeating, since gravitational has to come continuously.
Yes.
This is repeating. So this is coming at certain pulse because when
Okay.
this conversion is happens whenever it's perpendicular to this, other than it's small. So this conversion is happens only when it's there. But this gravitational itself is suppose instantaneous, say at the time produced at the time of some merger or something like that, which is very instantaneous. Now this instantaneous, and at the certain time, suppose this effect is also there. It converts there and it's happening just for once. You no longer have any input gravitations, you no longer have an output. Yeah. But what our idea by Maya and Amanda's take is that probably one mechanism doesn't work for all FRBs. You need multiple mechanisms eventually. So that's what our idea. And when Amanda said that, like, suppose you in future, suppose many FRBs have been detected, say thousands and more, then you need to put them in some classes. Say, for example, now people have just said repeating, non-repeating just from observations. But for say for supernova, we put lots of classes, 1B, 1A, different parts. So here also, we believe that eventually people will come out different classes, and maybe each class might be explained by different phenomena.
Okay, super. Well, thank you very much. We really appreciate the support. And then stop recording, please.